What did we learn about logarithms yesterday? Anything? Anything new for you guys? Talked about the common log, the natural log, who their bases were. Change of base formula, that was an important formula, true. When we look at a logarithm, what makes a logarithm really, 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 really easy to solve by hand without a calculator? Common base, yeah. If we can make the bases match, if we can make the base of the argument, if we can make the argument into an exponential function, if we can make that base match, psh, easy cheesy, lemon squeezy, don't even need to plug it in, right? However, sometimes it's not so possible. Thank you. Sometimes, sorry guys, it's really hot and stuffy, just hang in there. They're doing a lot of tours today. I'll try to open it back up in just a second. So the change of base formula is like, what if it's not working well? What if it's not working right? And people with the yellow button on your calculators, you're like, I can't even put it in my calculator until I use the change of base formula. And for others of us, it might be easier or even more possible to do by hand if we change the base. All that to say, there is the change of base formula, and sometimes it does help out. That's true. Sometimes it does help out. But not always. Not always. It's not always necessary. I'll put it that way. Why is the log of any why is the log of any base of 1 always going to be 0? Any base to the 0 power is equal to 1. So then we started talking about going between exponential and logarithmic forms. And that's very, 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 very helpful as far as solving, which remember, all these are rules that we're trying to figure out so that we can play with the puzzles. So if we do have an x stuck in a logarithm, how can we always get that x out? Undo the log with a to the power of. Or if we have an x and an a to the power of, how can we get that out? Undo the exponential with its counterpart log. Because remember, what's the relationship between logarithms and exponential functions? Inverses. They're inverses. They undo. Remember, they're each other's undoings. So if we ever need to undo a base to a power, like here, use a log. If you ever need to undo a log of, use a power. Okay? And that's what kind of hopefully helped you guys in homework last night, and that's where we were ending yesterday. But what we didn't get to talk about were the graphs. Okay, here we go. Basic graph of a logarithm. Wait a minute. A log is an inverse of an exponential. So what's the exponential graph look like? Whew. Swoop, there it is, right? Exponential growth. Have you ever heard a speaker talk about, oh, it's growing exponentially? That means it's growing really, 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 really fast, getting steeper and steeper, so it's growing, but by higher and higher increments. So a logarithm, guess what? He's not the opposite, but he is the inverse, meaning instead of growing super, super, super fast, guess what he does? He grows super, super, super slow. As you go farther into the graph, as x approaches positive infinity, the logarithm will grow, just like exponential, but it's going to grow slower and slower and slower and slower and slower. You can also think about that whole reflection over the y equals x line, if that helps. The exponential, like we kind of did a quick sketch of earlier. The a to the x is going to be growing fast. The logarithm is going to be growing slow. But what else do we know? Hey guys, what did we know about the exponential? When was x equal to 0? Or I should say, when x was 0, what was y? So if this had the point 0, 1, what's a logarithm going to have a point of? 1, 0. Good. So we have our y equals log base a of x. He takes the point of the exponential and flips him. That's another reason why any log of 1 is going to be 0, whatever the base. Hold on, exponential graphs. Do you remember the other special point? What was this special point up here? When x is 1, y is a. Yeah, so 1a would be on the exponential graph. And do you remember what the special point was over here at negative 1? 1 over a, because it flips the a in the denominator. So what can we put on the logarithmic graph? Instead of 1a, it's going to be a, 1. And instead of negative 1, 1 over a, it's going to be 1 over a, negative 1. So exponential graphs say, give me your power and I'll give you what results. Logarithms say, give me the results, and I'll tell you the exponents, or I'll tell you the powers. So exponentials say, give me powers, and I'll give you the result. Logarithms say, give me the result, and I'll tell you the power. So what's the domain of this log? Wait, one more graph characteristic. Exponential function have? Every exponential has a horizontal asymptote at y equals 0. Bless you. But every logarithmic graph is going to have a vertical, yeah, it's going to flip, a vertical asymptote at x equals 0. So let's fill in our characteristics. What's the domain? How left, how right does a logarithm go? A non-transformed logarithm. How left? Ooh, he's never going to pass. So 0. Including or excluding 0? So parenthesis. And then how right is he going to go? Yeah, positive infinity. Range. Ah, how low does he go? Where did he go? Oh, here he is. Say it louder, but I agree. Negative infinity. And how high does he go? Good. Shh. Oh, I'm wrong one. X-intercept. Yeah, good. So we can say 1, 0 or x equals 1. 1, 0 or x equals 1. Strictly monotonic. Remember that guy? We were talking like being really boring because I was talking about monotonic and how monotonic has to do with monotone, and monotone is someone who speaks in the exact same tone, the exact same way, and if I did this in class, all of you guys would fall asleep because I'm so monotone. What do I mean strictly monotonic? What doesn't change? The tone. What's the tone of a graph? Kind of. I mean, the curvature doesn't change either. The behavior. And what's the graph doing? Increasing. Yeah, it's the increasing, decreasing nature. So strictly monotonic, only x value on its domain. It doesn't switch to decreasing. It doesn't switch to constant. Only increasing the whole time. The vertical asymptote, we already talked about him. X equals 0. And logarithms are continuous. No, they aren't. They have a vertical asymptote. But the whole portion of the graph, this is the entire log graph. Are there any jumps, any holes, any breaks, any reason to pick up my pencil as I draw him? No. So he's continuous in his domain. Kyle.
I've been plugging in log into the calculator and getting this thing different. Like it doesn't keep going. It just stops. It's like it's just like it stops at one point.
Let's talk about that real quick. When you plug a log in, when you plug anything into your calculator, and the calculator tries to show you a good picture, do you remember how sometimes it's limited based on just the parameters of the calculator? Okay. Do you remember when we tried to graph, and it's been a little while, when we tried to graph, wait a minute, it's review, but guys, who is this guy? X squared plus y squared is 1. Who is that? Circle with a radius of 1. How could we put it in our graphing calculator? What did we have to do to put it in there? Hold on, what's the button that you hit to graph? Y equals. Who has to be alone? We had to get y by itself. And when we got y by itself, remembering the properties of absolute value, square root of a squared, we got plus or minus square root of 1 minus x squared. Can we start there? We know this is a circle. We know the radius is 1. So if we tried to get our graphing calculator to do it and to show us the circle in function mode, which it doesn't like doing, number 1, because circles aren't functions, we would have to put in oh, sorry, I'm in a very different mode for calculus right now. There we go. If we tried to put this in, we would first of all have to put in 2 different functions. We have to put in the positive square root of 1 minus x squared. And we'd have to put in the negative square root. So first of all, we'd have to put in 2 functions. You guys, oh, we okay? Okay. We have to put in 2 functions to make 1. That's a hint that it's not a function. That's number 1. But number 2, when we go to graph, I'm going to make my window zoomed in because this circle only has a radius of 1. So I'm going to go into like negative 2 and 2 just to make it nice and zoomed in. Negative 2 and 2. Some of these things are a little weird just because of a Calc BC thing we were doing the other day. How does the calculator do at graphing the circle? That's all right. Does it do perfectly? No. Number one, why does it look squished? Isn't it up 1 over 1? Shouldn't it look like a nice circle? But it looks like an ellipse. Why is it squished? Because the graphing window is a rectangle, not a square. So when you say go 2 and go 2, these two are going to be a different actual measurement than those two. So that's why there's this button called Zoom Square that makes everything nice and even. And then it makes it to where this one goes up 2 when this one goes out almost 3 or a little bit more than 3. It makes it nice and even. So the tick marks are the exact same now. But still, it's not a great picture. Why isn't it a great picture? Doesn't connect. But it should connect. Plug in x is -1 and you get 0. Plug in x is 1, it's 0. It should connect. It should go all. Why doesn't it connect? There are these little things called pixels. And the pixels say, I'm going to get closer and closer and closer and closer. And then suddenly it's like, I can't get closer, because if it got closer, it would go too far. The pixels limit it. So it's like, I'm not allowed to go past 1, so therefore, since I can't actually, a pixel won't let it move over anymore. It's like, all right, fine, I'm done. But what does our brain know about this graph? It is a circle. It's connected. So let's apply that to ln. Let's apply that to ln. I'm going to go zoom standard. I'm going to graph ln of x or any logarithm. When we go to graph ln of x, I'm guessing, Kyle, this is what's going on. Hopefully I'm right. And we graph. It hits? Wait. No. There's supposed to be an asymptote, isn't there? It's not allowed to hit. Let's zoom in. Oh, it's getting closer and closer and closer. But what I'm guessing you're seeing is if we make the window go down, so that we try to make it keep going. Let me go down to like -10 or something like that, and then we graph. Why? And if we were to zoom in, why does the calculator freak out right about there and seem just to give up, either give up or hit? Pixels. It can't get any closer. Look, that's right next to that. It can't physically get any closer. Now, if you were to do maybe the ones with colored lines, those ones might be able to get a little bit closer than my calculator, but still the same problem is going to exist in that to get closer and closer and closer and closer to some extent, or at some point, the physical nature of it with the instruments that we're using can only get so close, and so it's going to freak out. But what do we need to realize? It's going to keep on getting closer and closer and closer and closer forever. Cool? All right. Zoop. So what happens when we transform logarithmic functions? What if we start shifting? What if we start reflecting? What if we start stretching? Well, we're basically just going to use our graphing clues from before. Anything that happens on the outside is what kind of transformation? Vertical. Anything that happens on the inside is what kind of transformation? Horizontal. Good. Whenever you see addition or subtraction, what kind of transformation is it? Well, but what kind of transformation? Vertical, horizontal, what? Pause! Give everyone in your group a high 10. People are falling asleep. Don't do it on their heads, do it on their hands, but you have to wake them up to do that. Go. I know, the door is open, the tours are passed. Hang in there, the air will be coming. Don't hit their head. Just hit their hands. Wake them up to get the high 10. Here we go. Okay, add or subtract. What kind of transformation? We already talked about horizontal, vertical, but what's going on with the addition and the subtraction? Shifting, right? So outside, I'm going to have a vertical shift. B units. If B is positive, it's up. If B is negative, it's down. What's going on with my minus C? Horizontal. Shift. And yeah, Robbie, you're right. If it is truly a minus, it will be to the right. C units. A is going to be the base, which very similar to exponential functions. If the base gets bigger, it is going to end up stretching. It's an extra type of transformation with exponential and logarithmics. The base will always make or also make the stretch. Could you guys have like numbers multiplied? Yeah, you could. We'll deal with it. we're going to have a negative outside the logarithm, right? If we're going across the, wait a minute, across the x-axis, yeah, that's going to be an up-down, right? Across the y-axis, if we have an x in the negative, sorry, a negative on the inside next to the argument. Just things to keep aware of, or things to keep in. But the nice thing is, kiddos, just like all the parent functions in section 1.6, man, that was a chapter and a half ago, or 1.7, if we can have the parent function down, if we can have these 3 representative points down, can't we shift those 3 points if we need to, right? Can't we flip the signs of the y's or of the x's if we need to reflect? Can't we multiply the x's or the y's by numbers if we need to? So the first step to any transformed function and getting the graph is starting with the representative points, the key points of the parent function. So let's see what we can do with this guy. First things first. If you want, get out 3 colors. First things first, or 2 colors and a pencil. First things first, graph the parent function. Apply the general characteristics to log base 2 of x. Apply the general characteristics to log base 2 of x. I want you guys to get me at least 3 points. And an asymptote. I'm not giving you tons of time, but use the general characteristic, the general patterns that I showed you on the page before. Okay, I'm going to check your points, because if you don't have the right 3 points, it's going to be hard to do the transformations, right? So what's 1 point that you guys got for log base 2 of x? Good. Because every non-transformed logarithm is going to have 1, 0. That's going to be the same. What else do you got? Good. 2, 1, because it's the base 2. And if you plug in log base 2 of 2 to the 1, oh, the power 1 is my answer. So 2, 1. And what's another point? 1/2, comma, negative 1. Because log base 2 of 1/2 is log base 2 of 2 to the negative 1. The power is negative 1. This is my parent function. Oh, wait, how do I know to skim the y-axis? What else can I put? Good. X equals 0 is my asymptote. Okay. You're allowed to reach out in your groups if you want. I want you guys to graph G and graph H. Maybe 2 different colors. Graph G and graph H. Using the representative points of the parent function and using the asymptote. Those are good. It doesn't. Okay. Thanks, Rachel. If you haven't yet, reach out in your groups and be like, hey, we all doing the same thing? You might not be done, but you can reach out, work together. That's okay. I'm coming up in just a second. right. As I do the transformations, you guys tell me verbally what the transformations are. What's going on in G? You write 1? Good, but technically I would say write 1, then up 2 if we were doing the order correctly. So I'm going to go write 1 and then up 2. Got it. I'm going to go write 1 and then up 2. Got it. I'm going to go write 1. Oh, no, 1. That's going to be in the halves, huh? And then up 2. 1, 2. Got it. Wait a minute. What else should I shift?
Yes.
Ah, so write 1 and up. Well, I guess the up doesn't matter, huh? Did you guys properly get the graph of your transformed G? Maybe you could have even gotten the points if you needed to, because then to each of these you could have gone ahead and write 1 means add 1 to the x, up 2 means add 2 to the y. Yeah? Write 1 means add 1 to the x, up 2 means add 2 to the y. Write 1 means add 1 to the x, and add 2 to the y. Dun, 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 dun. Questions on G? Okay. So what's going on with H? Verbally, where are my transformations? Struggle. Not down 1 specifically because there's a plus, but we always end with our vertical transformation. So is there anything horizontal that's being messed up? No. But there is a flip times -1. Logarithm is being multiplied by a -1. So I do have vertical or horizontal flip. Vertical, which means all of my y's are now opposite, right? So all my y's are opposite signs, so I flip, vertical flip, and then I do what? Shift up 1. So I'm going to go ahead and flip 0. Oh, well, that's boring. Still 0, right? Flip the 0 and then go up 1. I'm going to go ahead and flip the negative or the positive 1 to be -1. So over 2, up 1, nope, down 1. Right? I'm going to flip and then what? Shift up 1. So this one was a flip, which didn't go anywhere. Up 1 ended up being the point 1, 1. This one, 2, -1, up 1, 2, 0. And this one I need to flip. So over, where is he? Here he is. Over a half down 1 is now over a half up 1. And then also up 1. True? So I had -1 becoming a +1, and +1 plus 1 is 2. So now I have 1/2, comma 2. What happened to my vertical asymptote? Flip it. Okay, well that's boring. And then up 1. Well, nothing. So it should have been the exact same vertical. Ah, where's my point? There he is. There we go. And there's H. Questions on H? Some of you might want to write down the actual transformations if you got a little stuck. For instance, this one is a vertical flip and then a shift up 1. Whereas this one, we went right 1 first, shift right 1, and then we went up 2. Are we good? I'm scanning. Okay. So transform logarithmic graphs. What did I say is the key to being able to do these two functions? Having the parent function, having the representative points, and the asymptote. And then just performing the proper transformations, maybe going back to section 1.7 to review if you need to. Sound good? Okay. Boop. Have we already talked about how the inverse nature of logarithmic functions make them reflections across what line? The y equals x. Do you guys really need this? I don't know. Maybe not. Maybe not, because I think we've already written it down. But if there's anything that you want to add, now's a good time. Logarithmic functions are inverse functions of the exponentials, as we've been talking about. So as such, log base 2 of x is just going to be the reflection of 2 to the x. So I guess if you ever forget what log base 2 technically do, 2 to the 1, and then just flip all your points. I guess if you ever forget what log values are, you can always just steal exponential function that is his inverse. What's 2 to the -1, 2 to the 0, 2 to the 1, and then just flip those x's and y's, and then you'll go ahead and get the point logarithm. That could be a little baby studying trick, like, oh no, what if I freak out and forget what logs are? Just further. Where's the 0.21? Silly me. What power I'm in, the exponential 2, 4. The logarithm. The exponential would have the 0.01, the logarithm would have the 0.10. The exponential would have the -2 1/4. 0.14. So if you ever needed to, if this one's easier than that one, actually get his points and then just flip, flip, flip. There he is. Okay, but we've talked about that a lot. Inverses, how the x's and y's flip, the reflections across the y equals x. These are inverses of each other because what matches? Don't say the power, the base. The bases match. Good. Quick question. Homework help. If you see an ln, are you going to freak out?
Yeah.
Oh, party poopers, don't freak out. What if later on in homework the e's and the ln's start happening? Guys, how on earth could they expect you to do this without a calculator? Yeah, because we have an x value, we plug it in, right? So we could say y is equal to ln of, if we're trying to plug in f of e to the -4. If it helps, we can think about y as f of x, plug in to the x spot, e to the -4. Well, I don't know that by hand. That doesn't make any sense. Wait, who is ln? Not 1 over e, but it is a log with an e. Second, the power of e is its base. -4. Remember? Oh, -4. Dun, 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 dun. But what happened? To be undone. Yeah, just -4. So do we need to freak out with ln as long as there's an e involved? No. Now, if there's not an e involved, what are you probably using? Your calculator. But if there's an e involved, no stress, no big deal. We got this. Any other homework helps? No? Oh my goodness gracious. All right, pause. Oh, go back? Yes, I can. If I can get this button to work. Work, work, work. Nope, I tried. Okay. Those of you guys that did start homework, I'm freezing. Oh, okay. Nope, now it's just mad. All right. Well, that still works. Kyle, I'm trying. It's just being mad right now. There we go. I'm going to freeze the screen for just 1 second, just in case I went too fast on that example. I am sorry. I was having a little too much fun, I suppose. But I am pulling up the homework. I have it here. I have it ready. Does anyone have something that they're like, yeah, maybe just a little bit of clarification would be nice on number such and such? Uh-oh. Is it the moment of truth hour? Oh, I don't want to do that. You guys remember what one of my keys to success in this class is? Being real. Okay, be real with me. There's no punishment involved. Maybe a slight little like shoulder slump, but besides that, I'll be fine. Who has started homework? 3.2? 3 people. Okay. So the likelihood of us having questions, my guess is the people that start homework, they're probably doing all right on it, right? Yeah. We do have a question, but pause, hold on. If only 3 people started homework, some of you don't even know what homework is, huh? Let me, hold on, Kim, I'm coming back. Give me 1 second. For those of you guys that haven't started homework yet, I'll pull it up and have you write it down in your homework spiral. Sound good? And then if we go over any questions today in class, like Kim has one, I'm coming right back to it. And if I go over that question, can you put it in the right spot in your homework? No. But go to your workspace in the back of your homework spiral and you'll have it ready. You guys can utilize that space too. It's great, just random space for work. So if I were you, I would write down the following homework assignment. Here you go. I have your Google Classroom open. And as I ask him what her question is, and as I get ready for it, and get a picture of it, etc., you guys can go to the back of your homework spiral and be ready, because maybe, if she has a question on it, you might too. Kim, which one?
Just want to get the notes that she did the graph. We have it 445. It says I don't understand what you did on the board. So
45. What's
the vertical flip and stuff we just did on the graph. I just want to get that one.
this one, right?
Yeah, that one.
Okay, why don't you come over to the screen while they're writing down the homework. Come here. And she was trying to visualize and say, okay, if this is the log graph, if I shift, and if I... Some of you are very good at visual, and so you can actually be like, okay, if I'm doing this, and I'm doing this, and I'm doing that, and you can make it match. But some of you, it might be smarter to start with the base, the parent function. They're all log base 3. Graph a log base 3 and actually do the transformations first and then try to match, because some of you aren't very visual, and trying to do that is going to be hard. Sound good? All right, get out of here. This homework is due on Wednesday. I'll see some of you at retreat this weekend. Bye, guys.
Only 4 more periods.